Okay, this is 9.3 in your textbooks, combining two functions, or dealing this time with products. Yesterday we talked about the sum and the difference of two functions. Today we're going to talk about when we multiply two independent functions. So the goal is to represent the product of two functions graphically and algebraically and to determine the characteristics of the product. So learn about the math. Jesse, can you read that?
In the previous section, you learned that music is made up of combinations of sine waves. Have you ever wondered how sound engineers cause the music to fade out gradually at the end of a song? The music fades out because the sine waves that represent the music are being squashed or damped. Mathematically, this can be done by multiplying a sine function by another function.
Okay, the function defined by g at x equals sine 2 pi x, and f at x is equal to 2 to the exponent of negative x, where x are all real numbers where x is greater and equal to 0 as shown below. Observe what happens when these functions are multiplied to produce the graph. So we have the two original functions here in blue and red. When they are actually combined together by multiplication, so the product of those two functions gives us the green graph, which makes a lot of sense just in this particular example, just looking at them, because we can kind of imagine how that blue graph being multiplied by the red one would create this diminishing effect in the combined function. Okay, the question is, can the product of two functions be constructed using the same strategies that are used to create the sum or difference of two functions? So before we ask ourselves that, who can tell me what's the strategy that we used yesterday with creating a combined function, either difference or sum of functions? What was the strategy? Who remembers from yesterday? Yeah. Yeah, it was points on the graph. We made a table of values, and what did we do specifically, Elijah?
You solve for y, and then you just add them together.
Yeah, exactly. So we got the individual y values for the original functions, and then we just added or subtracted them. Right? So when we ask this question, can we use the same strategies? What they're asking is, can we find now the original y values for the blue function and the red functions, and then multiply them, and then with the same x value, will that now be the y value of the combined function? Okay, and what we're going to find out in a minute here is it actually works out. Okay? So, example 1, it says investigate the product of the function. So here's the blue and the red function that we had over here. Okay, so we're investigating the product of these two functions, blue and red. Okay, so the first step we did, like we did when we did sum and difference of functions, was we found the y value for both the red function, or f at x, and g at x. Okay, so those are these values here. Okay, so notice how the x value stays the same. It's the same x value for f at x, g at x, and the product of f multiplied by g. Okay, that x value stays the same throughout. And now for the y values, we just take those two y values and multiply them. So 1 times 0 is 0, 0.84 times 1 is 0.84, and then we end up developing a table of values where we have our x values and our y values. Okay, and then we can just go ahead and graph those. Okay, when we graph them, we end up with this combined function. So pretty straightforward, pretty simple. We find the y values of the two independent functions, and then we multiply them to find the combined function y values. All right? And that's confirmed with a graphing calculator. All right, let's look at some of these reflecting questions. I want you guys to think about this. I'm going to ask you guys. So these are pretty simple questions. If the point 0.4, 0.76 of the f at x function and 0.4, 0.59 of the g at x function, what's the ordered pair that belongs to the product of f times g at x? What would be the point? If you don't want to use, if you know the answer and you don't have your calculator, what would you do? Yeah.
Multiply the y values.
Yeah, that's it, right? Multiply the y values. The x value is the same, so that's what we want. And we want to know the product of these two functions. So the product, it would be 0.4. The x value, again, as I said, stays the same. And your y value would now be 0.76 times 0.59. So I think that's 0.4484. Okay? So that would be your value in your product function. Okay? Next question. If f at 1 is equal to 0.5 and the product of f times x at 1 is equal to 0, what do you know about the value of g at 1? Alex, what do you think?
The value of g at 1 is 0.
Excellent. How'd you know?
That's 0.5 times 0 is 0.
Excellent. G at 1 is equal to 0. Why? Well, we know because 0.5 has to multiply by 0 to get 0. Okay? Good. Look at the original graphs of f at and g at x. How can you predict the locations of the zeros of the combined function before you construct a table of values or a graph? So we go back to here. Okay, we're looking at this graph. How can I predict where the zeros will be on my combined function, which is this graph over here? How will we know? Yeah?
Wouldn't it be the same as where the zeros on the sine graph is?
Yeah, exactly. Either, right? It'll be either the location where the blue graph hits 0 or the red graph hits 0. Because if the red graph hits 0, that's going to get multiplied by whatever the blue value is and vice versa. So our 0 values should be wherever the 0 values are in the original functions. So 0, 0.5, 1, 1.5, 2, 2.5. Okay? So if we look at that, we can see that those are our zeros on the combined function. Okay? So we're starting to develop or see a little bit of a pattern between the original functions and the combined functions. Although there's still not much, right? There's not any consistent really rules. We still need to take the y values and do the multiplication or the operation that's required. Any questions about that? Okay. What is the domain of f at x? F times x. How does it compare with the domain of g, of f and g? Okay. So the domain of this, we can see there's an arrow here and there's an arrow here, so we know that the domain here is XER. And how does it compare to the domain of both of these graphs? They're actually both XER as well. Okay, so it's the same. Okay, we learned yesterday, we went through it a little bit quickly, but we learned yesterday that the domain is dictated by the endpoints or the intersection of the endpoints of the two original functions. Okay, and we'll go into that more specifically with the next example. Okay. If function f at x was replaced by f at x is equal to root x, explain how this would change the domain of f times x at g. So remember, we can remember what the parent function of y is equal to root x looks like. Okay, who can tell me if this function here, which one is replaced? F at x. So if the red function was replaced by this, right? So we have now these two blue functions. What's the new domain going to be? Yeah.
X has to be greater than or equal to 0.
Yeah, why?
Because there's no negative values in it.
Exactly. Yeah. Because this function is undefined for negative values of x. So the product of this multiplied by this function would also be undefined. Undefined multiplied by anything is still undefined. Okay? All right. Example number 2. Determine the graph f times g at x given the graphs of x squared plus x minus 6 and x. So here are our two graphs. Here's our straight linear graph and our quadratic. We know from yesterday if we were doing a summation of these two graphs, it would just be a translation of the quadratic, so we'd end up with a quadratic, but this time we're doing the product of these two graphs, so we don't get that. We get this graph in green. I'm going to zoom in here. Okay, and the way we would determine the points of that green graph, again, we find our y values of the original two functions, f at x and g at x. And then we just go ahead and multiply those two functions. 6 times -4, -24. And then we take these x and y values and we create our plot, these points here. Okay, and then we extrapolate and interpolate between these points to create this green graph. All right, any questions about that? All right, so the domain of the product function is the intersection of the domains of f and g. And again, because f and g are both XER, the combined function is going to be XER as well. Okay, it covers all the x values. Okay. Any questions about that example? Pretty straightforward. Number 3. Okay, we have f at x is root x, and g at x is 1/2 x minus 2, so a linear function and a root function. Find the equation of the function f times g at x. So our solution again, we can either do our table of values, find our x values, and then multiply them. So in this case, they're just putting the functions together to find the formula. It just says find the equation. So we're just going to go ahead and multiply those two functions, root x and 1/2 x minus 2. Next, it says determine f, the product of f and g at 4. So we're just going to substitute in the value of 4 for x and solve. 0. Next, it says find the domain. The domain of g is XER. We know that because it's just a simple linear function. The domain of f at x is all real numbers of x greater than 0. Gennaro? Or sorry, Gianluca?
For the equation, how come they didn't expand it?
Here?
Yeah.
Because they weren't asked to. They were just said find the equation. They didn't say to simplify it. Okay? But you could have, and you would have had an equivalent. Okay? You would have actually had, no, it would have been on the numerator. No, it would have been okay. Okay, the domain of g is XER, but the domain of XER of f at x is greater than and equal to 0. So the domain of f times x, again, has to be all real numbers greater than 0. And that goes back to the first example we talked about, the undefined values. Okay? Finally, using graphing technology, graph and discuss the key characteristics. So one of the key characteristics we'd want to discuss on this graph. So the dark line is the combined function. So again, where the linear function crosses the x-axis here is the 0. It's also the 0 on the combined function. Okay, that's probably one of the only key points we could discuss. The other one, I guess, being is the fact that the combined function ends at the negative values. It doesn't go into the negative values. Okay? And that's because this function is undefined. All right, last one. Modeling a situation using a product function. The rate at which a contaminant leaves the storm sewer and enters a lake depends on two factors: the concentration of the contaminant in the water from the sewer and the rate at which the water leaves the sewer. Both of these factors vary with time. The concentration of the contaminant in kilograms per cubic meter of water is given by C at T is equal to T squared, where T is in seconds, time in seconds. The rate at which water leaves the sewer in cubic meters per second is given by W at T is equal to 1 over T to the exponent of 4 plus 20. Determine the time at which the contaminant leaves the sewer and enters the lake at the maximum rate. All right. So we want to find out the vertex or maximum point of the combined function by taking the product of this function and this function. Okay, that's what I got from the question. Okay, and that's what you need to get when you're given these questions. Okay, it's easy right now because we know we're doing multiplication. But later when you're doing a test in this chapter, it might be summation, it could be difference. You have to think about how would I find out that value. Okay? So our solution is, our CAT is in kilograms per meters cubed. So the first thing we need to do is convert all of our units so that we're working in the same units. Okay, so this will be familiar to you guys if you're taking physics. So you want to convert these units and make sure they're all in the same unit. So we want kilograms per second. The reason why we want per second is because our other function is dealing with time in seconds. All right? The product of the concentration function and the water rate function results in a function that describes the rate of the contaminant flow into the lake. So here we're multiplying the two product functions. Sorry, down here. Okay, so we end up with this equation here. C multiplied by W is equal to T squared over T to the exponent of 4 plus 20. We just take this function and multiply it by this function. Then they actually just use the graphing calculator to graph this, so you wouldn't be expected to have to graph this. Okay, and they find out the maximum point, or the vertex. Vertex, if it was a quadratic, if it's any other function, it would just be called the maximum point. Okay? And that's given by directly punching this equation into a graphing calculator and finding that value. Okay? And you'll find the time when it occurs and then the value. Any questions there? Alright, in summary. When two functions f at x and g at x are combined to form the function f times g at x, the new function is called the product. For any given value of x, the function value is represented by f at x times g at x. The graph of f at x, f times g, can be obtained from the graphs of functions g and f and g by multiplying each y-coordinate of f by the corresponding y-coordinate of g. Need to know algebraically, f times g is defined as f times g at x is equal to f at x times g at x. The domain of f times g is the intersection of the domains of f and g. If f at x is equal to 0 and g at x is equal to 0, then the product is also equal to 0. Similarly, if f at x is equal to plus or minus 1, then f times g at x is equal to plus or minus g. Similarly, if g at x is equal to plus or minus 1, then f times g at x is equal to plus or minus f at x. Any questions about any of this?